Alright, so this says Notes 4.4 Complex Numbers Day 2. Let's call this something else. This is actually going to be Chapter 4, Topic 10. And the lesson we're looking at is adding and subtracting complex numbers, or complex numbers, and solving by square root. So Chapter 4, Topic 10, adding and subtracting complex numbers and solving by a square root. Sorry about my horrendous handwriting there. You can ignore this day 2. This was set up differently last year, and this is not exactly how we're doing it. But we are looking at complex numbers, and we're looking at solving by square root. Let's first look at solving by square root. Now, for number 1, at this point, if we were trying to factor this and solve by factoring, we wouldn't be able to do this because this is not a difference of two squares. Alright, we can't do x plus 8, x minus 8. That would be x squared minus 64. We need x squared plus 64. So there is another way to do this, as long as we don't have, as long as we can get this x term by itself, then we can solve this. So let's get that x squared by itself, minus 64 minus 64. And we have x squared is equal to negative 64. And then we can take a square root to solve this. So to get rid of the square here, we can take a square root. And we can take a square root over here as well. Something to keep in mind, when you take a square root, there's two solutions. There's a positive solution and a negative solution. So I have to keep that in mind by putting a plus or minus sign on the outside. And the square and the root are going to cancel each other out. And I'm going to be left with plus or minus. If you remember this from the other day, the square root of negative 64 is not 8, but 8i. Okay, because the I takes care of the fact that it's negative, because this would be square root of 64 times the square root of negative 1, which is 8 and I, so 8i. So we have two solutions here. We have 8i and negative 8i. And those are our two solutions. Pretty straightforward. It's the same, it's pretty much the same as, well, not really. Let's continue. Let's look at number 2. So number 2, we have 4x squared plus 100 equals 0. Well, let's just solve this. So we're trying to get this x squared term by itself, so we'll subtract 100. And we will have 4x squared equals negative 100. Let's get rid of that 4, so we'll divide by 4 to do that. And we have x squared equals negative 25. Alright, well this now is where we have to solve by square roots. So we're going to square root both sides to get rid of that square. Don't forget, square roots have two solutions, a positive solution and a negative solution. So our solutions, we're going to have x is equal to plus or minus, square root of 25 is 5, and the square root of negative 1 is I. So this would be plus minus 5i. In other words, 5i and negative 5i. Or, of course, you could write it as a set of solutions, 5i, comma, negative 5i. Okay, you may see it like this as well, negative 8i and 8i. You may see it as a set of solutions as well, so that's possible too. Honestly, this, I don't care how you write it, as long as you know what you're looking for, as long as you know what we're talking about here, you can do it this way, this way, this way. This is if you are one of those people that want to be exact, this is the best way to do it. Set of solutions, do it that way. All right, number 3. We're going to get that x squared term by itself, so minus this 54. So we got 3x squared equals negative 54. Let's get rid of that 3. All right, so we got x squared is equal to negative 3 goes into 5 one time, and then 24 8 times? Yeah, negative 18. Is it really 8 times? Yeah, I guess so. All right, now at this point, we're going to take a square root. Don't forget about the plus or minus. So we're going to have x is equal to plus or minus. All right, now square root of 18, 18 is not a perfect square. So over here, let's figure out what the square root of 18 actually is. And to do that, we're going to break it into perfect square factors. So this would be 9 times 2, because 9 is a perfect square. So square root of 9, that's just 3. So we'd have 3 square root of 2, because the 9 can come out, but the 2 is still under there. So it's 3 square root of 2. So this is going to be 3 square root 2, but the negative sign, we need our I to make sure that it's a negative square root. All right, so I will write this as a set. So I have 3 root 2 I and negative 3 root 2 I. There we go. Those would be our 2 solutions. Doesn't really seem like it means a whole lot, but those are our solutions. They're complex numbers. They're imaginary numbers. They're complex numbers. All right, now the standard form of a complex number, because a complex number is a sum of a real part and an imaginary part. So sometimes you will have both. The A is the real part, and the BI is the imaginary part. So, for example, 3 plus 2i. This is a complex number. 3 is the real part, because 3 is a real number. 2i is the imaginary part, because 2i is imaginary number. Okay, so this is how your complex numbers, complex numbers will always look. The real part first, the imaginary part after, with an I on the end. So, how do we add imaginary or complex numbers? So, adding or subtracting complex numbers when they're in this form. Well, it's actually quite easy. It's kind of like combining like terms. The real part are like terms, and the imaginary part are like terms. So, for number 1, the real part, 5 and 2, we'd add 5 and 2, and then the imaginary part is negative 7i and positive 4i, we combine the imaginary parts. So this would bring us to 7 for the real part and negative 3i for the imaginary part. And that would be our simplified form when we add the complex numbers. All right, so you're just combining the real parts, combining the imaginary parts. I should put this in red like I did the rest of the imaginary parts. What about subtracting? Well, subtracting just means that there's a negative 1 that's getting distributed to both of these terms. So these terms are going to change their signs. So this is going to be, this is going to be the real part, 4 minus 3. So that's this and this. And then we have the imaginary part, negative 8i minus negative 6i, so plus 6i. All right. combine the real part, so 1 minus 2, combine the imaginary part, negative 8i and negative 6i is negative 2i. So number 2 simplifies to 1 minus 2i. Still a complex number. Alright, same thing for minus negative 1. So that would be 4 plus 1 for the real part. For the imaginary part, we have 6i, and then minus 2i. And then we combine each part. So 4 plus 1 is 5 for the real part. For the imaginary part, I have 6i minus 2i, which is 4i. So number 3 becomes 5 minus 4i. Alright, so adding and subtracting complex numbers is pretty straightforward. You just treat them as if they're like terms. The real part are a like term with the real parts, and the imaginary parts are like terms with the imaginary parts. What about if you have, this is something a little bit more complicated, if you have find the values of x and y that make the equation equal. Hint, set the real part equal and the imaginary part equal. A plus bi equals a plus bi. Alright, so we have 3x minus 5 plus y minus 3i equals 7 plus 6i. Alright, well the real part of the left side is 3x minus 5, because there's no I next to either of them, so they are definitely real. And on the right side, the real part is 7. So our real equation, the 3x minus 5 should be equal to the 7. What about the imaginary part? Well, the imaginary part is y minus 3. Now, I don't care about the I know that that's the same on both sides. But the imaginary part is y minus 3 on the left side, and it's 6 on the right side. So the imaginary part, we have to make y minus 3 equal to 6 for these both to be equal to each other. Alright, so these are pretty straightforward equations to solve. Plus 5 plus 5. I got 3x is equal to 12. Divide by 3, and we see that for the real parts to be the same, the x needs to be equal to 4. What about the imaginary parts? Well, this is a one step. We just have to add 3. So for the imaginary part to be correct, y needs to be equal to 9. And we can check that. 9 minus 3, that gives us 6i. And then for this other one, 12 minus 5, that gives us 7. So x and y must be 4 and 9 in order to make these the same or equal to each other. So let's look at another one. A little bit more complicated, it looks like, because we got some mess on both sides here. So let's see what we can do. First, let's start by identifying the real part and the imaginary part. So the real part on the left, we have 5x plus 1. And on the right side, the real part is 2x minus 2. How do we know it's real? Well, neither of these terms have an I next to them. For it to be not real, they would need an I next to them. So the real part, the 5x plus 1 on the left side, needs to be equal to the 2x minus 2 on the right side. Alright, not bad. That's definitely an equation that I can solve. Let's take a look at the imaginary part. So on the imaginary part, I have 3 plus 2y on the left side. We know that this is the imaginary coefficient because the I. And on the right side, I have y minus 6. And we know that this is the imaginary because of the I. So this, the 3 plus 2y on the left side needs to be equal to the y minus 6 on the right side. Alright, so we got two equations here that we need to solve. I'm going to move the 2x over here to combine it with my 5x, which will then turn this into a two-step problem. 3x plus 1 equals negative 2. I can subtract 1, and I will have 3x equals negative 3. I can divide by 3, and I see that my x must be equal to negative 1. Alright, let's do the same thing to find out what the y must be. So I'm going to subtract the y to bring it over here. So I'm going to have 2y minus y, so that's y, and then I'm just switching these. I'm going to put the 3 afterwards, and then equals negative 6. Alright, so 2y minus y is y, and then plus 3 equals negative 6. This is a one-step minus 3. So y is negative 9. Alright, so for these to make sense, for these two to be equal to each other, x needs to be negative 1, and y needs to be negative 9. Alright, so the homework is on page 51, 10 through 12, 17 through 26, and then page 52, 28 through 31.